So continuing with 8.4 with series, we are on geometric series now. Now if you remember, arithmetic series had that common difference, and it was addition, and geometric series are multiplication. So it has a different formula in order to find the sum of a geometric series or sequence. Okay, so there again we have the sum of however many numbers we're looking at. We're going to call it n. We take the first number, 1 minus the ratio to the first number, or to the total number of numbers we're adding, power, over 1 minus the ratio, where the ratio is not equal to 1. It has to be something else. Okay, so example 3 says find the sum of the first 10 terms of the geometric sequence, with the first term being 4. So my A1 is 4. And what else do I need? I need to know what my ratio is in order to do this. And the common ratio is -3. So this is going to be, what are we looking at? First 10 terms. So it's going to be that. My first number is 4. 1 minus my common ratio of 3 to the 10th power, which will always be whatever number this is, over 1 minus, and again my common ratio is -3, and we solve it from there. And when you solve this, you should get your -59,048. Okay, so that's what you should get. Don't forget to add those and add those because of the double negatives. Alright, so B, it is asking you to find, and let's get rid of the A portion of this. I guess it's only erasing part of it, isn't it? Okay. So B says find the sum of the first 8 terms of the sequence to 1/1/2. Okay, so I need to know what those 8 terms are, because at this point we've learned to find the ratio. Well, they gave us the ratio in A. They also told us what the first term was, and then we were able to solve this. So what you need is you need to know how many terms you're adding, what the first term is, and what the ratio is. When they give it to you like this, and they're asking you to find the first 8 terms, we know we're going to have s to the 8th power equals, in this case we're going to have 2 because that's our first number, 1 minus r. We don't know what our ratio is, but we do know that we have 8 terms over 1 minus r. Okay, so we have that much information to write the equation like that, but we don't know what the ratio is. So that's what we're going to be solving first of all. And what we do is we look at these first 3 numbers here and see if we can figure out what that common ratio is. How did we get from 2 to 1? Well, we took half of 2. How did we get from 1 to 1/2? We took half of 1. So I know my common ratio is 1/2, so I can put my 1/2 there, and I can go ahead and solve it from there. Okay, so let's jump into example number 4. Show that if regular payments of $1,000 are made at the end of each year for 5 years into an account that pays interest at 10% per year compounded annually, the future value of the annuity is $61.05. Okay, so what we're doing is we're showing that this is a true statement. So as we saw on the previous page, the future values of the individual payments into this annuity, which if you look under geometric series on the page previous, it talked about the annuities, and we didn't go over that because we're going over it in example 4. So we have our formula, and it's 5 years, and we have as our first number 1,000, and then we have 1 minus our ratio, which is 1.10, 10%, to the 5th power, because again, that's our n, and 1 minus our ratio there. And we're able to solve that. And when we solve it, we do get our answer 6105.10. That's our dollars. Okay, so remember when you're finding the ratio, it's going to be the interest rate plus 1. Okay, all right. So continuing on, infinite geometric series. I said we were going to get into this later. If we add the terms of an infinite geometric series, or sequence, we have an infinite geometric series. It is perhaps surprising that we can add an infinite number of positive numbers and get a finite sum. Now what we're doing is we're adding smaller and smaller and smaller numbers. We're not adding bigger and bigger and bigger numbers, because we cannot do that, because we can't go infinitely large, but we can go infinitely small. And what they're saying is okay, let's, for example, say that we want to take this distance and cut it in half. And then take that distance and cut it in half. What they're saying is, into infinity, we can, every distance that we're given, no matter how small, we can cut it in half. It keeps getting smaller and smaller and smaller into infinity. It never gets so small that it doesn't exist. So, anyway, that's kind of what we're looking at there. That's what they're talking about when they're talking about an infinite set of numbers. All right, so one of the key things, if you look on page 624 in the green, the sum of an infinite geometric series, they give you a formula for that. And the formula is 1 minus r, your ratio. Notice there's no number here because we're going into infinity, so there's not a set amount of numbers that we're looking at. But one of the key things they're saying is the absolute value of r must be a number less than 1. That's where we're talking about getting smaller and smaller and smaller. Okay, so r has to be a fraction. Okay, so there's our formula. And it does say also that if the absolute value of r is greater than or equal to 1, then the sum does not exist. Okay, so we're going to use that formula, and let's say that we are looking at example 5a. They give us 81 plus 9 plus 1 plus ... Okay, so there's something going on here. It looks like we're dividing by 9 to get the next one, divided by 9. That'll give us 1/9, 1 over 81. And, that'll just keep getting a number smaller and smaller and smaller, but it'll go on forever as we continue on here. Now, find the sum represented by this. If we were to take these numbers, and as we get smaller and smaller, we're adding smaller and smaller numbers to our answer. So there's my 3 numbers that they gave us. That was giving me what my ratio is. I just kind of kept going and found out, oh, my ratio is 1/9. And that is smaller than 1, so that will work. And I'm going to use this formula here to put that together. So S equals my first number divided by 1 minus 1/9. And in this case, it's 729 over 8. So don't even try to get your head around this. Okay, we keep getting smaller and smaller and smaller and smaller numbers. And if we were to add all the numbers up, that if each number as we go here gets divided by 9 all the way into infinity, if we add all those numbers up, we're going to get 729 over 8. Okay, so when I was taking this class many, many moons ago, I could not get my head around that. I did not believe it, and it doesn't do any good. You still have to do the work, so don't even try to figure it out. But maybe in calculus they will give you a little bit more explanation about this. This book doesn't really go into a whole lot more on that. Example 5b, and I could go into it, but God, do you really want me to take the time to go into adding those smaller and smaller numbers and show you why it works. Probably not. Okay, so this one here, this is the sigma notation for an infinite series. That right there tells you that you are going into infinity, so you're starting at 1 and never ending. Each new term results in one higher power of 2/3, that I there. So the common ratio is 2/3, and the 2/3 is less than 1, so it works. My first number is 2/3, so let's go ahead and write our formula here. And the formula is pretty simple. Okay, so 2/3 is my first number, 1 minus my ratio, and that gives me the number 2. Okay, so if I start at 1 as my exponent here, I get 2/3. When this is 2, this becomes 4/9. When this is 3, this becomes 8/27. Okay, we just keep increasing this number, 1, 2, 3, 4, into infinity, and we add all of the numbers together. And as we add all those numbers, we will get 2. Now, let's just real quickly kind of look at this. It kind of bothers me that you're not getting full on what's going on here explained. So that's 2/3. Our second, our 2 being in there for I, is going to be 4/9. Our 3 in there is going to be 8/27. Our 4 is going to be 16/81. Okay, let's stop there. Okay, and notice what's happening. Each time we go to the next number, our numbers get smaller and smaller and smaller. So we're still approaching 2, but very, very, very slowly as we continue on. So let's go ahead and change these fractions to common denominators. Okay, so that's going to be 27/54. That's 81/36. That's 81/24. Okay. Oops. A little dyslexic there, it looks like. And that gives me 130/81, which is actually 1.604. Okay? So we're getting closer and closer to 2. As we continue on, every number is going to be smaller than the previous one. So this is going to grow slower and slower and slower. And as this number gets smaller, this is going to grow more slowly until it almost stops because the number is so small. So we may be at, way on down the road, 1.988, and this goes on, maybe 4 million eights follow this. And then the next number we add, maybe the millionth 8 will turn to a 9. So see, it grows so slowly, and that by the time you hit infinity, you're at 2. And again, you never hit infinity, so it never quite gets to 2. But if there was an infinity, you would be able to get to the 2. So anyway, that's it for 8.4. So remember in the homework 7 through 10, you're doing geometric sequences, and 13 through 16, I already went over how to do that, all the way through 19 with the summations, and there's some story problems, and as you notice, I don't give you a ton of story problems, but I do want to make sure you get a little bit of an idea of what's going on with story problems, and that is it for 8.4.